And then
okay, so today I'm going to talk about our work on the duality between ADS3 pure gravity and Ising CFT. So it is based on a paper published last year, and there's a paper, another paper to appear. So these are my collaborators: Changming Zheng, Andreas Ludwig, Zhuxi Luo, and Zhenghan Wang. So before talking about the duality, let's first review what is the pure gravity on ADS3. So the 3D pure gravity has a very simple action. It can be written as the follows. So I write it in Euclidean signature, and the on-shell solution has a constant curvature. There's no local degrees of freedom, namely there's no gravitational waves. And if we focus on the negative curvature, namely the cosmological constant is negative, and now we're talking about ADS3. Besides the nature of no local degrees of freedom, we have some interesting objects called BTZ black holes. So these are discovered back in '92. So around that time, and since then, there are many incomplete attempts to study the 3D pure gravity. So it starts from the proposal by Witten that 3D gravity can be somehow viewed as a transformation theory with a non-compact gauge group. And later, Alex and Witten attempted to sum over different geometries to figure out the full gravity partition function. And in the spirit of holography, people are also trying to find the 2D CFT dual of it. And there are several candidates, such as the Liouville CFT, Monster CFT, etc. But these candidates all have some undesirable features, and it is still a hot, ongoing project to find them using modern techniques like bootstraps. So the most important prescription of the boundary degrees of freedom is proposed by Braun and Anu back in '86. So if we go to the asymptotic boundary of the ADS3 in this metric, it turned out that there are two copies of Versor algebras at infinity. So these are generated by boundary condition preserving diffeomorphisms, namely the boundary gravitons. And they have the same standard charge, 3L over 2G. L is the ADS radius, and G is the Newton constant. There are possible proposals to quantize them, such as the cojoint orbit for C larger than 1, and by using quantum groups for C smaller than 1. So this relation can be viewed as a precursor of ADS CFT because we have two copies of Versor algebras. And the Braun-Anu relation is true regardless of small or large central charge, and it stays true if you add more matters into the bulk. So the boundary degrees of freedom, the boundary gravitons, are Versor descendants of the vacuum state. And on torus, the partition function can be viewed as the trace over the Hilbert space after quantization. So if we look at the gravitational partition functions with a torus boundary, it can be formally expressed as the path integral. And one can do a semi-classical expansion in order 1 over C for large central charge. So these are called the semi-classical expansions. But what about finite C or small c? There's a pioneering work done by Castro, Alex et al. For quantum media 3CFT duality at genus 1 for central charge C equals 1/2 and 7/10. So their strategy is to first sum over the bulk geometries with the same equivalence class of the conformal structure to get the quantity denoted by Z of X with conformal structure tau. X is the 3 manifold we're interested in. And then we do another sum over the boundary matrix connected by small diffeomorphisms. So these are physically the boundary gravitons we have talked about. So at central charge 1/2 and 7/10, it turns out that the above expression of gravitational partition function is proportional to CFT partition functions of Ising CFT and tricritical Ising CFT. And the proportionality is finite. So our work involves 2 parts. So the first part is on handlebodies. By adopting assumptions of Castro et al., we calculate the gravitational partition functions on any genus handlebody. So why are we interested in those handlebodies? First of all, because the duality is incomplete without them, and it is important in multi-boundary wormholes and black holes. So I emphasize here that the multi-boundary wormholes here are Lorentzian wormholes, and later on we will talk about the Euclidean wormholes. And our work requires new mathematical results, which helps establish the duality. And we found that the pure gravity with C equals 1/2 is special among all minimal models. And all other central charge lead to difficulty in finding the CFT duals. And the second part of our work is on non-handlebodies, and we propose a prescription for them. And the key ingredient is that we use the dense surgery to label different topologies. So I want to pause here and see if there are any questions. Okay, so let's review the duality on the torus and the solid torus. So the simplest geometry or topology one can think of for ADS3 is the spacetime with torus boundary. So it has 2 key saddle points. The first one is the thermal ADS3. And the important feature of it is that the contractible cycle is a spatial cycle, and the time runs along the longitude. And another important saddle point is the BTZ black hole. So it is obtained from the thermal ADS by doing the S transformation. So the boundary conformal structure tau goes to -1/tau. And here, the contractible cycle becomes the time cycle. Back in 2007, proposed by Maloney and Wheaton, that all semi-classical saddles can be obtained from the thermal ADS3 by large diffeomorphisms. So one do a fractional linear transformations on tau by SL2Z element. So I need to point out that all the saddle points are topologically solid tori, and they are classified by 2 integers C and D, and denoted by M sub CD. So A and B have nothing to do with it because A and B are fixed up to an integer shift for giving C and D. And Here I just write down the metric for MCD, but it is not important for our talk.
I'm sorry, can I ask a question?
Yes.
How do you know that there are no saddles with other topology with torus boundary?
Oh, so now first we focus on the handlebodies. So basically we restrict to the solid Torah, and I'll talk about non-handlebodies for the second half.
You're saying there are saddle points with other topology,
Yes.
but are you saying they're not semi-classical? I'm just confused by the statement in the middle of your slide.
I should say that all semi-classical handlebody saddles. That's a more precise word.
Okay, and I guess this,
sorry, do you mind if I chime in?
Yes.
The statement that was proven was that with torus boundary, all semi-classical saddles are handlebodies and are the ones that are written on this slide. It's only a higher genus that there are saddle points that are not handlebodies.
Oh, yeah, that's right. So yes, you excluded like the cusp geometries and
yeah, there are non-smooth geometries that have either cusps or like singularities somewhere. But if you look for smooth saddle points with torus boundary, then the ones that you've written on your slide are all you've got. The non-handlebody stuff is, as you know, of course, only relevant at higher genus.
Yes.
But this is just to address John's question.
Yeah.
I see. So just to be clear, so you somehow rule out like complements of knots.
Exactly. With yeah, they can't have torus. Yeah, exactly. I don't want to. Yeah, we could talk about it more if you want. Yeah.
Okay, I guess I have a second question though, which is, if you're at such small ADS radius, why do you care about saddle points?
You mean for the small central charge?
Yeah.
So that's one main assumption is adopted by Castro et al. So they want to have some handle on how to do the summation and get sensible partition functions.
My impression is that we know other examples of gravity partition functions where sectors without saddle points are known to contribute.
Yes. So non-saddle, for example, for torus boundary, so those basically so one important one obvious non-saddle for relevant for torus is just torus cross I, but you have two boundaries from that. But if you want to get a single boundary, I mean, there are like separate manifold with torus boundary, I suppose.
Yeah, there's certainly lots of others.
Yeah, they are addressed recently by Henry Maxfield and Hawking Togliatti in their paper, where they view them as the so-called KK instantons, but they are very unstable configurations. So those are Seifert manifold with torus boundary. That they are definitely contributing. So their contributions are obvious, are significant for near the extremal black holes and with high spins. But by far there's no intrinsically 3D computations of their contribution. So that is some uncharted territory.
Okay, thanks.
No problem. So as John said that one important assumptions by Castro et al. Is that we still view the gravitational partition functions as summation over semi-classical saddles. And the key observations there is that one can single out a vacuum seed, namely the contribution from the thermal ADS3 denoted by ZVAC. And then the other contributions from solid tori after SL2Z transformations can be just evaluated as ZVAC with argument transformed by an SL2Z element. And then one do the modular sum. So one naively think that the summation will be over SL2Z, but it turns out that it is too naive to assume that. Because semi-classically, there's a symmetry T which sends tau to tau plus 1, so that the ZVAC, the vacuum seed, stays invariant. And it turns out that for the quantum regime C smaller than 1, the symmetry is further enhanced. So it is enhanced to a larger SL2Z subgroup gamma C defined by keeping the ZVAC invariant. So it has a finite index in SL2Z. It implies that we have only finite number of saddles instead of infinite number of saddles as when C is large. For example, in the fairy tale, in the black hole fairy tale work in 2000 and by Melanie Witten in 2007. So mathematically, precisely speaking, the summation is over the cosets of SL2Z, the cosets of gamma C in SL2Z. Then the full gravitational partition functions can be written as a summation over those cosets. So the vacuum seed matches the minimal model CFT vacuum character squared. And the square basically comes from the fact that we have 2 copies of Virasoro algebra. And in the 2011 paper, the only possible candidates are Ising CFT and tricritical Ising CFT, because all other at all other central charges we have more than one modular invariant. So there's no well-defined duality between the gravity and CFT. So for Ising CFT, it turns out that the gravitational partition function is 8 times of the Ising CFT partition function. So let's have a one-slide review of Ising CFT. It is a simplest minimal model, and there are 3 primary fields: the identity, the spin operator, and the energy density. And they satisfy the following fusion rules. And on torus, the Virasoro characters are individually known for the 3 primary fields. And the torus partition functions is a summation of their modular squared. And back in 80s, people have studied the partition function on Higher and it is written in terms of the Riemann theta function or Siegel theta function instead of the Jacobi theta function on torus. And here, the argument tau, the complex structure, is generalized to omega, the period matrix of the homogeneous Riemann surface. And the mapping class group SL2Z of torus is also generalized to a homogeneous mapping class group. So mapping class group is the group of isotopy of the homeomorphism of the homogeneous surface. But the key issue is that the vacuum character is unknown due to there's no definition of global time on the homogeneous surface. And based on the gravitational argument, we propose a corresponding vacuum character. So I will talk about the duality on homogeneous. So the homogeneous enjoys several motivations. So first of all, is that it encodes the Lorentzian multi-boundary wormholes. So there's a procedure of analytically continuating the Lorentzian spatial slice into the boundary of the Euclidean space-time. And for example, in the following pictures, we have the thermal ADS3, the 3-sided wormhole, and one thermal ADS3 plus one BTC black hole. So the green curves in the pictures correspond to the t equals 0 slice. And the homogeneous surface also contains information on the CFT correlators. And there's a nice paper on the conformal block fairy tale by Alex and his collaborators. And finally, for sure that it is important for the complete duality. So just as a definition, the handlebody is topologically bounded by the Riemann surface in R3. So our strategy for homogeneous surface is that we first identify the vacuum seed as C equals 1/2 for the Ising CFT. And then we assume, so this is our key assumption, that the vacuum seed homomorphically factorizes for any surface. So it is a natural extension of previous work done by Ising and Matt Hedrick's et al. And then we write the full gravitational partition functions as a modular sum. It is over the right coset space. And as I mentioned before, the gamma C is defined as a group which keeps the vacuum seed invariant. And then we apply the TQFT techniques to prove that the modular sum is finite, and the modular invariant is also unique. So the uniqueness comes from applying the Schur's lemma on the irreducible representations of the mapping class group. And then we conclude that the two partition functions are proportional on any genus.
Do you mind if I ask a question actually about that last slide?
Sure.
So when you have a torus boundary, so I'm a little confused about the logic that lets you identify ZVAC as you know, the sort of contribution, the sort of perturbative contribution that would then be summed over capital gamma. When you have a torus boundary, there's a separate argument that you can make because there's a Lorentzian Hilbert space interpretation of the phase space as being two copies of diff S1, and then you can quantize the phase space, and you can argue, based on those papers you cited earlier, that the quantization of the phase space gives chi-vac. But I don't know of an analogous argument at higher genus. So is this just, are you just sort of asserting? Yeah, so is there an additional logical step that allows you to identify the seed as ZVAC? It's certainly plausible, but I'm not aware of a different argument.
I'm actually about to talk about that in the following slide.
Oh, okay, thanks.
Okay, thanks for the question. So yeah, so this slide will provide the intuition behind the first bullet point. So for genus G handlebody, we can stretch them into a long cylinders, G+1 long cylinders with two caps. So it can sort of viewed as the propagation and scattering of the boundary gravitons. And because we stretch the cylinders to be very long, it is at low temperature, and we can somewhat view the long directions at local time. And then the spatial slice, which is the shaded disk in the picture. So there are G+1 disks, and we expect that the quantization of the Virasoro algebra at C equals 1/2 still holds. So these Virasoro algebras are the Brown and Newell ones. And so based on this observation, we propose that the vacuum seed as the modulus squared of the vacuum block. So it is sort of a generalization of the identity block of the Ising CFT on torus. And so to make connection with previous work, we can consider the pinching limit, where we pinch off each long cylinders one by one. And there's another work I didn't cite here, which is by Dagraf and Erkverlind and Hermann, that by pinching off these long cylinders, the homogeneous partition Ising safety partition functions can be reduced to genus lowered by 1. Based on the paper by Singh and McHedricks, we assume that it is still true for small c. So I wonder if that answers Alex's questions.
I mean, I agree. It's certainly the most plausible thing one could write down.
Okay. So so this is the last two, the last one of the last two slides for handbody. So once we know the seed, we can write down the modular sum just as before on solid torus. So like on the solid torus, this modular summation is organized by this finite dimensional representation of the mapping class group. And we know the transformations of the characters on the mapping class group. So this, it turns out that the representation is a projective one, represented by the conformal blocks. And it also encodes the MCG actions on the finite dimensional Hilbert space of the 3D Ising TQFT on genus G handlebodies. So this Hilbert space is spanned by this span in this handlebody with admissible labels. And so there are very technical discussion about this representation, and we found that it is a irreducible representation, and by applying the Schurz lemma, we can view, we can find that there's only unique modular invariant constructed from this modular sum. So the proportionality between the gravitational partition function and the safety partition function is holds for any genus. And in the last slide, I just talked about the explicit genus 2 calculations. So we propose that the ZVAC has the modular squared of this Riemann theta function. So key feature here is that the first characteristic vector A1, A2 is a 0 vector. So it is just the same as the characteristic vector being 0 in the Jacobi theta functions for torus. And we checked that the Ising CFT partition function on the boundary of this long cylinder limit is dominated by Kivec squared. And it also satisfies the factorization upon degeneration. So the degeneration limit is a different limit from the pinching limit. So it is for genus 2, you just degenerate the genus 2 into 2 separate torus. So it passes several sanity checks, and in the end, that we input the ZVAC in Mathematica, and we got 3,840 modular images, and the summation of those images gives us 384 times the partition functions of Ising CFT. So that concludes my presentations on handlebodies. So next, I'll talk about non-handlebodies. So again, it enjoys several motivations. First of all, again, it is sensible saddles for ADS3. And furthermore, it encodes some important Euclidean wormholes. So the pioneering work is done by Madasina and Maus. that one can quotient the 3 hyperbolic space by some Fuchsian group or quasi-Fuchsian group. So if one quotient by a Fuchsian group, one get 2 identical asymptotic boundaries, and quasi-Fuchsian group, you get 2 different shapes. And then this year, in the attempt to address the factorization problem of 3D gravity and the possibility of ensemble average of CFT being the dual, Kohler Jensen studied this non-saddle non-saddle point, torus cross-line interval. So it is obviously a non-saddle because this geometry has 0 curvature. And there are some discussion on the stability of those Euclidean wormholes, and it involves other topics which I will not address here. And I need to point out that we focus on the single boundary case instead of these 2 boundary cases. So it turns out that our single boundary will be viewed as some kind of folding of the 2 boundary cases presented here. So the outline for the rest of the talk is that, I also need to point out that the non-handlebodies are notoriously hard. It has been studied analytically by Seeing and numerically by Henry Maxfield and his collaborators by some finite element analysis. And the novelty of our work is that we use the dense surgeries to label different non-handlebodies. And then we sum up different topologies because so we view those the non-handlebodies obtained from different dense surgery up to Kirby move as different topologies. So within each topology, we need further sum over the hyperbolic geometries, just as we did before. So I need one slide review of dense surgery. So dense surgery is a very useful and powerful technique to generate new topology on an existing topology. So first we cut out the tubular neighborhood of a knot. So the tubular neighborhood is just a thickening of a knot, so it is topologically a solid torus. And second, so this solid torus has the canonical disk bounded by the meridian. So then, just as shown in the picture below, on the right side, I denote the disk as a red one, and then we glue the boundary of the disk back into the knot complement, so that the boundary of disk matches some simple closed curve on the knot complement, and the simple closed curve can be parameterized by 2 integers p and q in the homology basis spanned by meridian and longitude. And thirdly, we fill the void by the 3 ball, which is the tubular neighborhood of knot minus the disk we just glued in. So pictorially, it can be drawn as follows. And the quantity P of Q is called the slope, and or equivalently, we call the procedure we just did as a surgery on a P of Q framed knot. And of course, we can do it on links. So so now, because we consider different topologies, so the gravitational path integral should have another sum over topologies on top of the summation of a hyperbolic geometry. So the summation of topology is denoted by some subscript x. And so intuitively, we should assign less weights to more complicated topologies. So the second interval over the geometries is connected by the boundary gravitons, so which is the integral over gx. So that's the the integral over boundary of x. So because we would like to label different topologies by dense series, we can rewrite the above path integral into the following one. So the first summation becomes the equivalence class of links. And the second summation becomes the summation over different geometries. I will explain these notations in the next slides. And the third, the integral represents the summation over the fluctuations of the boundary gravitons. The equivalence class of links are defined by Kirby moves defined on three manifold with boundaries, because one could have the same topology obtained from surgery on different links. So there are some criterion tells you which two different links gives you the same topology, and they satisfy this Kirby move criterion. So in order to explain the notation in the red equation, I need to involve the Solvent theorem. So it is based on a long series of work by mathematicians from 1930s to 1960s. So for an open three manifold X, there's a one-to-one correspondence between its marked conformal structure on its asymptotic boundary and the hyperbolic metric on its interior. So it is somehow generalization of the Mostov rigidity to infinite volume. And physically, we can view that the boundary gravitons provide some more degrees of freedom. So those will correspond to this marking structure. So by Solvent theorem, we have this relation: the space of all hyperbolic geometries is the modular space times across this marking. So modular space is the usual space of conformal structures. So this marking is a right coset of the 3D mapping class group of the space-time in the 2D mapping class group of its conformal boundary. So it is in one-to-one correspondence with saddle points at large central charge. So just for an example, for genus 1, handlebody, which is a solid torus, its 3D mapping class group is Z, which equals to our previous symmetry group in semi-classical regime, gamma sub infinity, which is generated by the T, which sends tau to tau plus 1. So in the rest of the talk, we will focus on the special class of non-handlebodies, namely the twisted eye bundles. So I want to pause here to see if there are any questions.
Maybe just to help me understand, in the previous slide, does that provide a classification of non-handlebodies?
It can enumerate all possible non-handlebodies, but it is very hard operationally.
Because it would involve classifying all links as well as.
Yeah, you need to first figure out the link on which you do the surgery. And,
okay, thanks.
Yeah, no problem. So for the buzzword for the marking is just it is coset of the 3D mapping class group in the 2D mapping class group. So let's see what is twisted eye bundle. So it is a synonym of non-trivial interval bundle over some manifold, but with opposite orientability. So what does it mean? It means that for an oriented base, the TIB will give you non-oriented manifold, and on the opposite, if you consider TIB over an unoriented surface, it will give you an oriented three manifold. So it is true for for any dimension. And the simplest example is that the trivial bundle over the circle is just an annulus shown on the left, and the non-trivial bundle over the circle is a Mobius band shown on the right. And for the if the base is a surface, then there's a unique TIB for each unoriented surface. So one exception is Klein bottle, which has 2. So the genus for unoriented surface defined as the number of RP2 in the connected sum. So more precisely, the TIB over the G+1 copies of RP2 connected sum together is a 3-manifold with a single boundary sigma G. And there is no contractible cycle in the TIB. So this is the most opposite manifold to handlebodies you can get. And there's another point of view on this TIB. So first, let's go back to the Mauthausen-Mauss wormhole. So it is H3 quotient by the Fuchsian group. And it has 2 asymptotic boundary, which are Riemann surface at genus G. And topologically, the 3D geometry is interval across sigma G. And the Fuchsian group is just the fundamental group of the asymptotic boundary. And the entire 3D space has a hyperbolic metric, and the hyperbolicity comes from the Riemann surface at higher genus. And this this X tilde double covers the TIB we just talked about. So the covering map is a composition of P and I. So P is a parity, and I is a fixed point free involution. So why it is fixed point free? So naively we can view the TIB as some kind of Z2 folding of the above manifold, but it will be too naive because we will get some singular point at the middle, and then we need to resolve the singularity by demanding that the I is fixed point free. So this I is non-trivial, but it always exists for genus greater than 1. So next we construct the TIB over the genus 2 unoriented surface from surgery. So the genus 2 unoriented surface is 3 copy of RP2 summed together. And because RP2 is a Mobius band capped with a disk, capped off with a disk, and then the disk surface, which is a connected sum of torus and RP2, is the once punctured torus glued with a Mobius disk. So you cut out a disk from the torus and you cut out a disk from the RP2, and then you glue them together. So the resulting TIB will be the trivial interval bundle over the once punctured torus glued with a non-trivial interval bundle over the Mobius disk along the common boundary cross I. So the thickened once punctured torus sigma 1,1 cross I is a genus 2 handlebody, and the TIB, the non-trivial interval bundle over Mobius disk is a solid torus. And the boundary of the once punctured torus is denoted by alpha. It's just a circle, and it is a 1,2 curve on the solid torus, which is the TIB over the Mobius band. And then it turns out that if we do the one surgery along the core of this M tilde cross I, it makes it, will render it as a standard solid torus, D2 cross S1. And then if we glue the standard solid torus to the thickened once punctured torus along the separating curve of the genus 2 handlebody, it will still gives you a genus 2 handlebody. So basically, in these 3 bullet points, we we show the procedure which turns the TIB to genus 2 handlebody. And then by figuring out the surgery procedure which turns the genus 2 handlebody to TIB, we just need to reverse the process. So it turns out that the link we need to do surgery on is this blue curve in the genus 2 handlebody. And the framing is shown to be -2. And we can generalize this procedure for TIB over any genus non-oriented surface. So for the oriented surface, which is the which has all genus, we have the first diagram as a survey diagram. So the derivation is basically identical to the previous one. And for the TIB over unoriented surface with even genus, it is slightly more complicated, but it turns out that the survey diagram consists of 2 links, one in blue and one in green, as shown below. And our assumptions on those non-handlebodies is that we still assume that the vacuum seed factorizes, which is the key assumptions we adopted before. And there's a further important assumption that the gravity as strongly coupled regime behaves like a TQFT. And we know the behavior of the TQFT partition functions under dense surgery. So by adopting this assumption, we can calculate the strongly coupled gravitational partition functions on TIB or other non-handlebodies from the partition functions of gravity on the handlebodies. And now we no longer have a well-defined, a very clear definition of ZVac, the vacuum seed, because for non-handlebody, especially with only one asymptotic boundary, it is hard to view what is the Euclidean time. But we propose the definition of the ZTIB instead of ZVac as the partition function of TIB given by the surgery on the most reduced frame link in a handlebody. So previously I talked about the extended Kirby move, which tells you under what circumstances 2 different frame link gives you the same topology. So within that equivalence class, we need to go to the most reduced one. And now the ZTIB is invariant under the enhanced symmetry group, just like before in the handlebody case. So it will be some enhanced version of the 3D mapping class group of our space-time. And then finally, by applying this summation over cosets, we can enumerate all the saddles, and we can do the summation over geometry. So the last step is guaranteed by the Solvent Theorem I previously invoked. So it is powerful, but it works like a black box.
Can I ask a question about that?
Sure.
So you've given a definition for what you call chi-TIB.
Mm-hmm.
Does that definition hold? Like, does that apply at arbitrary central charge? Yeah.
So it's a good question. We only did the some example calculations for genus 2 as central charge 1/2, and Yeah,
And just so
haven't
just so I understand correctly, the definition is that you start out with the handlebody, the conformal block appropriate to the handlebody, and then you perform surgery on that handlebody and
Yes.
transform the conformal block according to the usual TQFT rules. Is that right?
Yes, and the transformed chi will be some superposition of some labeled conformal block in the handlebody.
I see. So it's a superposition of the higher genus conformal blocks.
Yes.
Because they transform among one another when you do this link surgery on a link.
Yes,
I see.
exactly. So
okay.
so Alex anticipates my next slide. So here I just show genus 2 calculations. So previously we see that the genus 2 TIB, the twisted eye bundle, can be obtained from the surgery on the genus 2 handlebody. And then by invoking the TQFT rules, we can resolve the previous surgery diagram into this eyeglass diagram by using the R and F moves. So I think since it is a UQM talk, I presume that most of the audience are familiar with R and F moves. So it turns out that for TIB, we have this relation that the corresponding characters for the 3 primary fields becomes the superposition of the conformal blocks in the handlebodies. And then again the seed. Oh, sorry, I should have written down ZTIB instead of ZVEC. So ZTIB would be the modulus squared of the chi TIB. And so more explicitly, if we write the conformal block in terms of the Riemann theta function on genus 2 surface, it will become the last equation in this slide. And then again, so this will be the seed serving as an input. And then we again found out the 3,840 equivalent images. And the summation of the modular images will be the 96 times the Ising partition function.
Yeah, sorry. But once you know that chi TIB is a linear combination of the conformal blocks, it's automatic. It reduces just to your previous calculation, right?
Yeah, somewhat. Yeah, we recycle the same code.
Right. So it's sort of right. Okay. Thanks.
Yeah. So okay, so there are some remarks that so I won't talk too much about the first bullet point. The first bullet point is just even for solid torus, you can generate a non-trivial topology by doing surgery on a knot, as long as the knot is not inside the 3-cell in solid torus. You can generate a Seifert manifold, which is already constructed like 100 years ago. And so the second remark is kind of subtle, because the density can somehow modify the geometry to some extent, but it cannot generate all of them. We cannot collapse the double summation in the path into a single one. So we have to first sum over topology, and then we sum over geometry. So this is the feature instead of a bug for 3 manifold with infinite volume. So for 3 manifold with finite volume, there's a renowned Thurston Perelman theorem that geometry and topology are in one-to-one correspondence, but in the infinite volume, it is more subtle than that. So once more, as I mentioned in the previous slide, that the MCG machinery will do the job of enumerating geometries. And again, here I'm just repeating myself, that the enhanced 3D mapping class group will have some finite index in the 2D mapping class group on its boundary. So this summation over topology is has some kind of a revival recently in 2D gravity, like when people study the baby universes, like the genus expansion of JT gravity, and also the replicable wormhole geometries. So the outlook is that, so first of all, we still need to make sense of those sort of mysterious prefactor in front of the Ising partition functions. And then in our first paper, we didn't conclude that the duality for high genus still holds for tractive Ising because we don't know how to regularize them. So it would be an interesting question to regularize the tractive Ising on handlebody at higher genus. And another question is that in our previous summation, the summation of a topology, it is not obvious that the summation will be convergent because in 2D JT gravity, this summation will be asymptotic and namely divergent. And we should investigate more on the relation between geography and gravity. And for the first summation over the topology, I think it may be helpful by doing numerics because we know that with a powerful computing capability, people have enumerated like millions of knots. But the difficulty that we're in handlebody instead of S3, so there may be some subtlety there. And there's a further extension of the ADS CFT to ADS BCFT, which is talked about in paper just appeared with Andreas Karch and Zhuxi Luo. So there we only consider the parent 3D manifold at genus 1. So there are some more possible work to be done there. And also, can we do a similar similar formulation for spacetime with multiple boundaries? And that will be all I want to talk about. Thank you for your attention.
All right, thank you, Haoyu. Let's see, we had a couple of questions in the talk. We have time. Maybe we could do like 5 more minutes of questions. If anybody wants to ask, just go ahead. Maybe I can ask a very basic question to get started. I just have a question about, at the very beginning, when you want to calculate this gravitational partition function, you know that you have to do some kind of sum over geometries with some measure. I just have a question about the steps that lead from that to this summation over these CFT characters. Maybe you could just, for non-experts, maybe say a little bit about that logic there.
So I guess you mean this slide?
I guess I meant even back at the beginning.
So the logic is that let me see. I need to. So logic is that we have different semi-classical saddles in the partition function, and so first we figure out the contribution from one of them, which is this vacuum seed. So I guess your confusion is on this vacuum seed. So it is the contribution from the low temperature ADS3. And by figuring out that, one can just do the modular transformations to generate all the other saddle points.
Okay. Are there any other?
Yeah, I have a question. So you showed that these other non-handlebody contributions that you summed also, under the assumptions you made, contribute a multiple of the Ising partition function. So in some sense, one might have thought that the existence of other contributions might mean that you get additional terms other than the Ising partition function. Is it clear that if you compute some other observable, that these other geometries will always give something proportional to the answer you already got from the handlebodies?
So for handlebody, we basically only calculated the partition functions. So because it is a pure gravity, and it's hard to make sense of the what is the correlation functions, like the bulk boundary propagators and boundary to boundary propagators. But I presume that one can artificially add some method to the bulk and do the calculations. We haven't done that yet.
I see. I have another question actually. So, so clearly, a theory of gravity is a topological field theory in that it doesn't depend on a choice of geometry because you're summing over geometries. But is it clear that the individual contributions to the gravity partition function, that like a contribution that comes from a particular sector, is it clear that those have to individually satisfy the rules of 3D topological field theory, like you're using?
Oh, that's a good question. I haven't really thought about that. But so let me see.
Maybe, yeah. Can I actually also follow up on that? Because I also have that question. Because it seems like the idea that all you need to do is take a linear combination of the handlebody blocks to get a non-handlebody contribution. I guess I'm just not quite sure if I see the logic underlying that. Because like one of the things that this surgery does is, well, okay. As you know, one of the things that this surgery does is change the topology. So for example, you could take a sphere and you could take the complement of a knot on a S3, and one metric you could put on that is the Euclidean BTZ black hole, for example, which is a handlebody. But then you could do a surgery on that of this type to change that into a different handlebody. So we don't, and so to me, that seems to indicate that this knot surgery would include things like the sum, like the action of the mapping class group. Right. So it's not. So it's. So I guess I'm kind of asking the same question John is asking, which is why, the TQF, like why you're treating perturbative gravity, which is the thing that's supposed to compute Z TIB on this slide, as a TQFT. Because it's supposed to be a perturbative expansion around a saddle point, not a sum over saddle points. It's exactly, I guess it's exactly John's question.
So for the knot complement example, I think because it is a finite volume 3-manifold, then the surgery will definitely change the geometry. Right? So it somehow plays the role of mapping class group transformation. But for the infinite volume, it should be more subtle than that.
Okay, thanks.
No problem.
All right, maybe this is a good time to wrap up. So let's all thank Haoyu again, and I will turn off the recording, and then we'll see you all next year.
Thank you.